So first, a little introduction to operating systems. So here's a quote from the Computer Science and Engineering Research Study from 1980, so almost ancient history by now. And it says, operating systems are those programs that interface the machine with the applications programs. The main function of these systems is to dynamically allocate the shared system resources to the executing programs. There's a continuation of the quote that's in the notes that says the interface with adjacent levels continues to shift with time. Functions that were originally part of the operating system have migrated to the hardware, and program functions extraneous to the problems being solved by the application program are included in the operating system. So the clear definition of operating system is sort of hard to come by because, well, ultimately operating systems are what we make of them. Still, let's talk about the details that are relevant for this course. Yeah, if you've ever met Linux users, they are definitely likely to recommend their preferred operating system. Okay, but I mean, what does an operating system do, really? I mean, it's a piece of software, sure, and it sits between the hardware of a computer and the applications, the programs that run on this computer. So between the hardware and the application programs being the kind of thing that we wrote in previous courses, notably including ECE 252. Now, the operating system does many different things, and it has goals, and the goals can conflict with one another. Right? Sometimes the goal is about using the resources efficiently, but sometimes that conflicts with the goal of using things fairly. But the goal of the operating system is not to run for its own sake. Its goal is to see to it that other programs can operate efficiently, providing an environment for those other programs, but maybe also collecting and reporting some data about what is happening and what has been happening. And it needs to enforce policies that are defined by system administrators. And so here's a quick sort of structural diagram of the modern computer. And down at the bottom we have our hardware devices, I/O, networking, memory, system bus, execution hardware, things like the CPU. And we have our application programs, our libraries and utilities up in the software area, and then the operating system sits at the bottom there, connecting between, well, the application program and the execution hardware. And we've spent a lot of time writing application programs and asking them to call on things using the application binary interface, which is effectively a system call. And, well, we're going to spend lots of time talking about how those things work sort of from the other side now. Now, the operating system is responsible for resource management and allocation. Ultimately, any resource like CPU time or memory space is limited. We might have a huge amount. It might seem an incredible amount as compared to what it was 10 years ago or 40 years ago, but it's still limited. The operating system does have to decide how to allocate these resources, and it is responsible for keeping track of the allocations of those resources so we understand what's currently in use and what is not. And in the event that there are conflicting requests, well, the operating system chooses the winner. It decides who gets that resource. So if two programs want to use the printer right now, the operating system gets to choose, okay, which program wins. How it does so, we'll talk about a little bit later on. And I mentioned that it doesn't run for its own sake. And that's important, right? It's there to enable other useful programs like, say, Photoshop or Microsoft Word or whatever it is you want to run. Any computer system that you have has various pieces of hardware, CPU, memory, I/O devices. I/O devices even include monitors, keyboards, stuff like that. And the operating system is responsible for abstracting away the details of this so that program authors do not have to worry about the specifics. Imagine how painful it would be if you had to write Hello World differently for different hardware because, well, if you want this to appear on the console and you want that to appear on the monitor, those require different instructions on different physical machines. We don't want that. Right? That's pretty terrible in terms of developer experience, and the idea of not having to do that sounds pretty attractive. And part of the goal of the operating system is to stop you from needing to do that. Now, any modern operating system that we are likely to talk about has the concept of multitasking. That is, more than one thing in progress at a time. Yes, we can go back to look at old computers from the mid 1980s, in which it ran exactly one thing at a time, and there was no such thing as time sharing. But those are not really what we're going to talk about in this course. Maybe a little bit when we talk about embedded systems, but it's not something that we're likely to talk about in great detail. And that means that resources are shared. CPU time is limited, and CPU is shared between all of the processes that are running currently on the computer. And the operating system is responsible for creating and enforcing some rules, because this is a source of conflicts. And not all interaction is necessarily conflict. Sometimes processes want to cooperate and not compete, and the operating system can help them to do that as well. And we've seen some examples of that, right? We've seen some ways in which we can ask the operating system to allow, say, memory to be shared, which allows programs to cooperate even though they might normally compete. So we have different goals, right? And one goal may be to use the computer hardware efficiently. And here's an example of an IBM supercomputer. And supercomputers cost a huge amount of money to build, and they're not exactly cheap to run either. And part of how their life is funded is by, selling CPU time. And selling the CPU time requires, of course, that you have customers who want to use it, but there are customers who are interested in this, right? If you're doing like a weather situation, simulation, if you are trying to do some physics simulation, something like that, it is how you do it. You just rent time on a supercomputer. And when the supercomputer is not doing this useful work, that's time you could be selling that you're not, and that's money that you're not making that you could be making, and you probably need to make that money. So selling that CPU time necessarily implies that you want to sell as much of it as possible, and that means that you would try to have an operating system that manages this system to try to maximize CPU usage, right? This is one kind of operating system, and we frequently focus on operating systems that look like the ones that we're familiar with, right? Your phone, your laptop, those are a certain kind of operating system, but in this course we are going to consider things like supercomputers, but we're also going to consider things like embedded systems, and we're going to consider things like real-time systems. And all of those are equally valid forms of operating system, but they have different goals and they behave in different ways, so it's important not to extrapolate too much from direct experience with, say, Windows on your laptop. Operating systems do tend to be large and do a lot of things, and when you get an operating system, we expect it comes with a web browser. That might not be a good web browser, and it might not be the one that you choose to use, but it comes with it, and you use it solely for the purpose of downloading one you prefer better. It probably also comes with an email client, it comes with a text editor, but none of those are the relevant parts that we are interested in talking about. We are interested in talking about the kernel. And the kernel is the core. It's the portion of the operating system that is always present in main memory. It's the central part that makes it all work. And the kernel is the focus here, not the programs that ship with the applications and the applications that come with it. Operating systems do evolve over time. There will be new hardware released, there will be new types of hardware, there will be new services added, there will be bug fixes, and other miscellaneous new features that sort of go with the operating system on its own. Evolution is, however, constrained. And it's important to maintain compatibility for programs, right? If a user upgrades his or her desktop operating system and a program breaks, even if that's the program author's fault, the user blames the operating system vendor. Windows is a good example. You can see they have pretty strict devotion to not breaking binary compatibility up to a certain point. And Linus Torvalds, yes, the person that the Linux kernel is named after, gets unreasonably angry with people if they submit a kernel change that might break user space programs. And yeah, I mean, his swearing and ranting on the mailing list is kind of legendary and is not exactly an example of good management that I would like to suggest that you follow. But certainly he's well known for this. How obsessive are operating system designers? Well, consider this example, which is admittedly from more than 25 years ago, about Windows 95. Yes, 95 as in the year 1995. Now, I recognize that this is also ancient history, but the game that you see here is called SimCity, and this was a very primitive version of SimCity as compared to the ones that you could play more recently. But here's a story about it running in Windows 95. So the quote, and it's linked in the notes if you want to read the whole thing, says, Windows 95, no problem, nice new 32-bit API, but it still ran old 16-bit software perfectly. Microsoft obsessed about this, spending a big chunk of change testing every old program they could find with Windows 95. John Ross, who wrote the original version of SimCity for Windows 3.x, that's the version that preceded Windows 95, told me that he accidentally left a bug in SimCity where he read memory that he had just freed. Yep, it worked fine on Windows 3.x because the memory never went anywhere. Here's the amazing part. On beta versions of Windows 95, SimCity wasn't working in testing. Microsoft tracked down the bug and added specific code to Windows 95 that looks for SimCity. If it finds SimCity running, it runs the memory allocator in a special mode that doesn't free memory right away. That's the kind of obsession with backwards compatibility that made people willing to upgrade to Windows 95. So, as we proceed, we will focus on Unix and Unix-like systems. We'll mention Windows here and there where it's appropriate. This is for practical reasons, right? There's only so much time, and Unix-like systems represent a large percentage of the operating systems out there, including Linux, Mac OS, Android, and some more. This Windows example, though, is just sort of a well-known story about how obsessive operating system designers can actually be in terms of making sure that the user experience is not affected by the operating system upgrade. And then there's the real-time part of the puzzle, right? And if you listen to the doctor, he will tell you that it's wibbly-wobbly, timey-wimey stuff, which, yeah, I mean, that's maybe not the most dignified way to explain it, but that's what he says, right? People assume that time is a strict progression from cause to effect, but from a non-linear, non-subjective viewpoint, it's more like a big ball of wibbly-wobbly, timey-wimey stuff. You heard it from him. He's a Time Lord, and who am I to argue with him? No, really. What we want to talk about is what is a real-time system? What makes a system real-time versus non-real-time? And real-time systems are one where wall clock deadlines actually matter. And real life is full of systems, many of them embedded systems, that operate on the basis of meaningful deadlines. Some common examples of real-time systems include aviation, anti-lock brakes, industrial machinery, video conferencing, satellite launches. All of those are real-time systems because the wall clock deadlines matter. If we get it wrong, then we don't necessarily get the outcome that we want. Right? There are deadlines and there are consequences for missing a deadline. Here's the first of many examples where maybe I can't say the caption out loud because it involves some bad words. But when we talk about real-time systems, right, we say that they deal with tasks. And task is just a way of saying something that needs doing. And tasks are divided into a couple of categories, and we call them hard and soft real-time categories. If a task is hard real-time, then a late answer is useless. It has a deadline that has to be met to prevent an error, prevent some damage to the system, or for the answer to make sense. If we're trying to launch a satellite into orbit, if we don't have the calculation of when to fire the thrusters that are ready in time, the calculation is not useful and it needs to be repeated. If we are trying to calculate the position of an incoming missile, a late answer doesn't do us any good. If a task is soft real-time, the task has a deadline, but it's not, strictly speaking, mandatory. If we miss it, there's maybe a consequence, but it's not the end of the world, right? It degrades the quality of the response, but it's still doable. If decoding a frame of video takes longer than expected, we miss the window, the video quality and the viewing experience are worse, but the video is not totally ruined. You can keep watching. It's not the end of the viewing experience. There's going to be a lot more about real-time systems later on. In most topics, we'll talk first about sort of real-time systems in general, and we'll build on it a little bit to see what complexity or differences the new constraint of real-time will add.